Okay, welcome back. I hope you all had a nice lunch. So we're going to have our second invited talk, and it's a great pleasure to have Ambrus Kaposi here from the University of Budapest. He's going to talk about strictification of categories with families.
Thank you. So I don't need a microphone, right? Thank you very much for the invitation. It's a great honor. I'm very happy to be invited. So this is a joint work with Loic, who's sitting there. You can also ask him questions. And this will be a practical formalization talk, okay? So type theory at its best. And I only have 17 slides, so feel free to stop me in the middle anytime for questions or clarifications. Okay, so the usual question, what is type theory, can be answered in lots of different ways. There's this axis which goes from syntactic to semantic. So we have actual implementations of type theory like Agda, Koch, and Idris and Lean, where there is some inconsistent meta language in which we implement a type checker. There's no typing relation. The information that is inside the typing relation is implicit in the type checking algorithm itself. But it actually works. These things actually work. Then there is extrinsic syntax, where we introduce typing relation, which carves out the meaningful terms of all the preterms that are there in the actual implementation. And there are lots of formalizations based on this, based on extrinsic syntax. So here you have inductively defined the notion of preterms, then typing relation, conversion relation, usually also reduction relation on top of this. And type theory is defined as this complicated beast of all these different notions together. Then you can go towards semantic by introducing intrinsic syntax. So unquotiented abstract syntax trees. That means that now you only have meaningful terms. You don't have meaningless terms anymore. The terms are indexed by their types, but you still have a conversion relation, which is explicit, and you have rules that it is a congruence with respect to all operations, and it's an equivalence relation. And then if you go even more semantic, you get a notion of type theory, which is an algebraic theory. So for example, CWF is category with families. So you have a category, which we think about it as the objects or the contexts are the type theory. The morphisms are substitutions between these contexts. And then you have two more sorts of types and terms, which we actually want to describe in such an algebraic setting. But this is semantic in the sense that you have so that your theory is an algebraic theory. So you have a well-behaved notion of model, homomorphisms between models. The models form a category with nice structure. You have free models and co-free models and all these kind of things. But in the CW, in the category with families, you're still a bit close to the syntax. And then if you want to go a bit more semantics, you can replace the type indexing of terms. So in CWFs, for every term, you don't have just a set of terms. For a context and the type in that context, you have a set of terms in that context which have those types. In natural models, you replace this by a map from terms to types. So it's not an indexing anymore, you have a map. So it looks a bit further away from what you would expect from an implementation at the top of the slide. Then you can go even more semantic by using comprehension categories, where you just have two categories, one which contains the context, the other which has the types, and then you have some maps, fibration between them, explaining the connection of context and types. Or you can use locally Cartesian closed categories, where you use slice categories to express the local dependency of types on context. So And so if you go upwards, you get something more practical. You have observable computations. If you go downwards, you get elegance, abstraction, and arguably easier meta theory. So you can prove things about the things at the bottom easier. I should have said that in the top, we usually, like here we talk about the syntax, so that's why it's also syntactic. So what is the syntax down here in the semantic setting? So from CWFs, we usually consider the initial model or the initial algebra as the syntax, which exists by general categorical abstract nonsense. And so, for example, for CWFs, this is intrinsic quotient ASTs. You can think about them that way. So you have abstract syntax trees, which can only be plugged together in well-typed ways, which results in the fact that you only have well-typed meaningful terms. And moreover, you quotient all these abstract syntax trees by the conversion relation. So two syntax trees which represent the same semantic thing, they are equal in this setting. And the same below as well. If you go upwards, you have more ad hoc choices. So for example, you have to decide whether I use named variables or De Bruijn indices or De Bruijn levels or locally nameless or some other representation of variables. You have to choose whether you use typing a la Curry or typing a la Church. These kind of things don't even make sense down here. You can only talk about them at the top. Or you have to decide whether you use economic typing rules or paranoid typing rules. And there are all these kind of interesting details. While if you go downwards, you have forced, some choices are forced. So for example, from CWFs and below, all of these notions use De Bruijn indices essentially, or some kind of combinators which implement De Bruijn indices. Or they use explicit substitution. So up here, substitution is usually defined operation. So the substitution is what appears in the beta law. While down there you have some built-in operations and equations explaining how this substitution behaves. So and an interesting example of a meta theorem which might be easier downwards, but it was a normalization. But normalization is interesting because it wasn't clear. It was not clear how to define normalization for type theory in this abstract setting for a long time. So normalization means that every term can be reduced to a normal form. So my stupid example is that here is a term which has a red x in it, this lambda x, x dot x applied to successor of 0, so to the natural number 1. And it's deep down in the term, hidden under two successors. And this can be reduced to just the natural number 4, right? And then the normalization says that all these red x's can be get rid of, and then in the end you get a term which doesn't have any reducible expressions in them. And this is used for implementations in type theory in type checking, because when you check whether a term has a correct type, you take the two types, the one you inferred from the term and the one you want to check against, and then you reduce both of them. And then if the result is the same, then you are happy. That thing is well timed. But actually, you can expect. So in more abstract settings, it's difficult to say what normalization even is. Or, I mean, it can be difficult in principle, but actually you can do it. So in the CWF setting, so in this category with families, which was in the middle of the diagram, actually I will talk about CWFs because that's in the middle. So I intentionally made my slide so that CWFs are in the middle. So you can define normal forms inductively by this mutual definition of the so-called neutral terms and normal forms or values. So a neutral term is either a variable or a neutral term applied to a normal form, and a normal form is either a neutral term or a lambda expression. So this is for like type theory with only functions in it. And then you can, if you have more type formers like Booleans, then the eliminators go into neutral terms and the constructors go into the values. And there's a pattern on how you can do this. And then there's a function which goes from normal forms in context gamma of type A into terms in gamma of type A. which kind of like quotes a normal form or says which term this corresponds to. And then normalization can be specified as a section of this function. So that means that you have a function from terms into normal forms. And because and if you take a term, you normalize it, and then you go back, you get back something which was equal to the original term. So now these terms are quotiented by the semantic conversion. So it's actual equality that you want to get after the normalization. And because normal forms are an ordinary inductive type, you can do type checking because they don't include any quotient. You just check if you have two normal forms, you can just look at them and check whether they are the same. Okay, and so in this kind of reduction-free setting, I mean, if you look at a book on type systems, then it's all about reduction relation and typing relation and type reduction preserves typing and these kind of things. So in this more abstract semantic setting of CWFs, you don't have to consider reduction. Everything is well typed. Everything preserves the equality, and you can even define normalization this way. For simple type, this was done in the 90s, but it took quite long to get this work for dependent types. And the main idea was to use proof-relevant logical relations, which are also a different name for categorical gluing. So these and then since then there were now that's kind of the standard to prove normalization for a type theory. You use a kind of gluing argument, and it's very abstract, very short, and beautiful on paper. But so far, no, these gluing arguments haven't been formalized or computer formalized. So there are several formalizations of type theory in the extrinsic style, where you have the typing relation and reduction. Even the most recent one on lean, this lean for lean, it's also done in this extrinsic style. And these more semantic normalization proof, they are basically non-existent. Even if there are some CWF-based formalizations in Agda or Koch, they are very difficult to use. So the question is, what is the reason for this? Well, one issue is that you need quotients to even define what the syntax is. So we said that the syntax is the initial model in this abstract setting. And it's actually some kind of quotient inductive type. And most proof assistants don't support these QIITs. So that's one reason for this. And then there's the issue called transport hell. So I will tell you a bit more about this. So an analogy for transport hell is the following. When you use a proof assistant, then it's advised that you always use lists together with proofs of the lengths of the list rather than vectors which are indexed by their length. So vectors are really difficult to use. So here's the standard example. We want to define a reversal function on vectors. So vec an is a vector of length n, which has elements of the type A, okay? And this is how it's defined. So if we have an empty vector, we reverse it very easily. We just return the empty vector. If the vector starts with an x and then it continues with xs, so this x is an element of type A, then what you do is you do a recursive call, you reverse the rest of the vector, and then you concatenate the singleton vector which only has x in it, okay? So you put the x in the end, essentially, and then you continue recursively. So there's an issue with this definition. So the issue is that it doesn't make sense. Why? Because the things on the two sides have a different type. So here I promise that I go from vector A of length n to vector A of length n, but I get as an input a vector of length 1 plus n, and the output is n plus 1, because here I put it at the end, okay? So actually what you have to do is you have to transport the output along commutativity of addition for natural numbers. So you refer to commutativity of addition. And this is itself not a real problem. The real problem starts when you start to prove things about this reversal, which uses a transport. So for example, that it's involutive, you want to prove it. And then it's easy to prove that it's involutive for the empty vector. But when you want to do it for a vector which starts with an x, then, well, you can do a recursive call, and that's easy. But then the question mark here, this is just transitivity of equality, says that reversal of a transported thing is equal to something else. So now here you need to prove a lemma to prove that reversal commutes with certain transports, and you have to do this by hand. Loic showed, or Loic told me that it's impossible to have an algorithm which pulls and pushes out these transports all the time, because it makes equality checking undecidable. I mean, maybe you could have some tactics which help you with this, but okay, so that's the transport help problem. And then another disadvantage of intrinsic syntax, or this kind of semantic syntax compared to extrinsic syntax, is that certain things are propositional rather than definitional. I said that in this on the top of my first slides, in those representations, you usually define substitution by recursion on the term. So, for example, if you have an application, you apply T to U, and then you substitute it. You just get the application on the recursive calls, and this is a definitional equality in most of those above systems, but in this CWF style nice semantic system, it's just propositional, and you have to do more work. Whenever you have a propositional equality, you have to prove it. Okay, so this talk is about solving these problems. So the first one is the easiest. You can just use cubical type theory or observational type theory, which can be implemented via rewrite rules in existing systems, and those support quotients and quotient inductive types. So we are happy about this. And actually, the second and third problem, we will solve them at the same time. So the solution is to make the equations in the syntax definitional. So let me give. So how can we do that? So first of all, why is it good to make them definitional? So if commutativity of addition was definitional for the definition for working with vectors, we wouldn't have this problem because we wouldn't need to transport it. So and it's the same for the more complicated system of type theory. If the equations are definitional, then there are no transports and there's no transport hell. I will give another example of transport hell, which will be more impressive than the vector one. So one solution is to just use extensional type theory, and we know that extensional type theory is conservative over intensional type theory with Panaxt and UIP. So actually, we are happy using extensional type theory, and actually this is what we do on paper all the time, and this is why all these pen and paper gluing proofs work very well. Okay, we don't want to do that. We could use rewrite rules, but that's an extension of, so we could say that all these equations that we want to be definitional, we add them as rewrite rules, but then again, we use a different kind of type theory, so we change our meta theory. And what we are doing instead is that we will replace the weak model, so we have this initial model, which is weak a priori, and we want to replace it with an equivalent stricter model. This is why the title of this talk was Strictification. So I give you some analogies. So the programming analogy is that in the Haskell prelude, difference lists are used because concatenation of lists is only propositionally associative. And this leads to inefficiencies. Why you can replace a list by list, you can represent a list by a list or row list function, which just takes an input list and puts the list that I mean in front of the input list. Okay, and because these are just functions, you can compose these functions, and function composition is definitionally associative. So you have a better behaved notion of list. Okay, and in fact, this is just an example of the Yoneda lemma. So the Yoneda can be used to strictify categories. So you replace the morphisms between J and I by Yoneda J, by natural transformations between Yoneda J and Yoneda I. And because natural transformations are just functions, if you compose them, they are, it's just ordinary function composition, and that's also definitionally associative. So actually any category can be replaced by an equivalent, even isomorphic, strict category, where by strict I mean that associativity and identity laws of categories are hold definitionally. So I guess this is a technique that should be used in all category theory formalizations in type theory. So what are not examples of what I mean is the things which are usually called strictification. So the splitting of comprehension categories by Hoffman using right adjoints, or the local universes method, which uses left adjoint for the same thing. So these take model of type theory where substitution is only, the substitution laws only hold up to isomorphism and make them hold up to propositional equality. Instead, what we want to do is to take some model where certain equations hold up to propositional equality and turn them into definitional equalities. Okay, so that's the goal of this talk. And actually, on my first slide, the models at the bottom, they were weak models in the sense of this, the non-examples. So they had substitution laws up to isomorphism rather than equality. And what do we get out of this? We get better behaved models. So let me show you what the difference is. So this is algebraic theory. It's a generalized algebraic theory, CWF. So this is the substitution calculus of type theory. It seems a lot, but it's not that bad. So you have these contexts and substitutions. These are the object and morphisms of a category. Then you have all the category stuff, composition, identity, and the categorical laws. You have a terminal object, this diamond. And this epsilon is the empty substitution into the terminal object, which is unique. Okay, and then you have two more sorts of types and terms. And you have type substitution. So type is actually a presheaf. So it's a functor on this from this category of contexts and substitutions into set. And you have the functor laws. And then you have a kind of dependent presheaf of terms, where if you have a term in context gamma of type A and you substitute it, then you get a term in context delta, which was the domain of the substitution. And then the type is also substituted. And here comes the beginning of transport hell, that the functor laws for term substitution, they are transported over the functor laws for types. So we can't even state these equations without knowing these equations before. So this is a general phenomenon for generalized algebraic theories, or essentially algebraic theories, when later equations only make sense because of the existence of previous equations. Okay, and then this triangle is the context extension operation. So a context is either empty or it contains some types using this triangle, and then this triangle has a universal property which is described by these other laws. And note that here is also a transport, and here is an even more difficult transport because this is a transport over transitivity of two equalities. Okay, and this is what I call a weak CWF. And then the strict CWF, look at the difference. So if you look at this equality, it becomes three equations. So it becomes definitional rather than propositional. And at the same time as making the equations definitional, the transports disappear, because if an equation is definitional, then transport over it automatically, like it's a transport over reflexivity, basically, and then it disappears. So this is a much better behaved notion. You need to talk about this, you need a kind of two-level type theory. So actually what we do in Agda, we can only talk about weak CWS because we don't have access to the definitional equality of Agda while we are programming in Agda. We can observe it, but we cannot state it as a type unless you have two-level type theory or something like that. So actually in this project, we use two-level type theory informally, and whenever we work in Agda, we have to work with the weak CWS. Okay, so my example of transport hell is saying what it means that CWF has Boolean types. So model of type theory supports Booleans. So you have this bool as a type former, and because it's a closed type, if you substitute it, it's as if you didn't do anything. So bool substituted by gamma is the same as bool. So actually this gamma is an implicit argument of this bool, but we don't write it out. So what happens when you substitute a bool? You just change this implicit argument, okay? Then you have the constructors true and false, and then you have the induction principle. Okay, and you see that the substitution equations for the constructors, they depend on the substitution rule for the type. So that's why these transports are here. And then there's the induction principle with the beta rules. So if you apply the induction principle to true, you get the first argument. If you apply it to false, you get the second argument. But then to even state the substitution law for the induction principle, you need to do quite a lot of work, you see. So if you have the induction applied to all these arguments and then substituted by gamma, it's the same as induction where the substitution goes under the arguments. So you see that this one has to be transported, and the second one has to be transported twice, and there is this alpha, which is some kind of general law that if you have a type P, which is substituted by U, and then gamma is the same, you can like swap the two. So you can first substitute with some lifted version of gamma, and then the U, which is also substituted. And actually, when you want to prove this, so, and this is only to specify what Booleans are. So this is, we haven't proved anything about this type theory. We just want to say what it means to have Booleans. And look at how we prove this alpha. So it's quite a lot of steps. I mean, I'm sure you can abstract away some of this and develop some theory to make this nicer, but this is really typical to when you work in transport hell. So like you can tell the PhD students, be a real man and work yourself through transport hell, but it's really difficult. So here I'm just pointing at something. So here, so like half of these steps are actually using equalities. Like this is functoriality of type substitution and so on. But then lots of the other half of the steps are transport rules. So for example, what we do is here we use, this is how a commutation law similar to how you commute the reversal of vectors and transport. The transport can be pulled out. In the same way, if you have a substituted type and there's a transport on the substitution itself, you can also pull the transport out the same way. And then you need to use like a relationship of transitivity and transport and so on. And sometimes the transports just disappear. Like, for example, here, there's this type U substituted by gamma, and then it's transported along this equality. And actually, this equality happens to be something equals the same thing, and then it disappears because it's just reflexivity. So, but this is the kind of work that you need to do, and there's no insight from this work. It's like Andreas Saber said, this is like burning brain energy without any outcome. There's no reason to do this. While if you have in a strict CW, if your CWF was strict, you can specify substitution strict Booleans. So substitution strict Booleans means that the substitution laws are definitional, okay? But the computation laws are only propositional, and there's no issue here, no transports visible anywhere, and it's a really nice place to be in when you are formalizing with this. Okay, so now I will tell you how we do this. So actually what we are doing is we take a weak CWF like this, and we convert it into an equivalent strict one, which if the original one has weak Booleans and the output one has this kind of substitution strict Booleans. And intuition comes from higher order abstract syntax. So we all know that presheaves over a category form a model of type theory. They form a CWF with pi types for any C, so for any category C, okay? And if C itself is a model of type theory, then in the internal language of this presheaf model, you have this tie, which is a set, that is tie is a presheaf, and you have terms which which is a family of sets over type in this internal language. Externally, it's some kind of dependent family of presheaves. So internally, you have somehow access to the types and terms of this, the base category. And moreover, if C supports pi types, then this universe is also closed under pi. So this chi and Tm, these kind of, so a type and a family over it, we usually call them universes. And this is what it means that the universe is closed under pi type. So pi types now take a in pi, and then the fact that the second type depends on A or can involve A means that the second one is a function from terms of type A to types. So actually what's happening here is that this pi, here the substitution calculus, is modeled by the meta-theoretic function space, so the function space of the presheaf model. And we can make this completely precise by, I mean, this function space of the presheaf model is nice. I mean, if you are in the internal language, then you use Agda as the internal language of the presheaf model, and in Agda functions are definitionally associative. They are well behaved, and we can make this completely precise by formalizing a model of type theory internal to presheaves over C, where the contexts and substitutions are just sets and functions of the meta theory, and then the types and the terms come from this universe. So types in gamma are maps from gamma to this red tie, which came from the base category or the base CWF, and terms again are maps from gamma to these terms, the red terms, which come from the base category. And then, for example, pi type is also defined by the red pi, and the substitution is just function composition. So all the substitution calculus comes from the meta theory. And actually, all the substitution laws that I complained about before, they are all definitional in this model. So this is a substitution strict model, and we call it the contextualization of P. It's called contextually. It's Raphael invented this name, contextualization. Raphael is sitting over there. Because what you do, you have a kind of universe, this tie and Tm, which doesn't have context. And then you create a model which adds context. So basically what you do is you add context to what you started with, to this universe. Okay, but all of this happened internally to this presheaf model, and now we want to do this externally and not use some internal language magic. Yeah. Okay, so sorry, and does this end at proper 3? Okay. Yeah. Okay. So okay. So what I will do at the next slide is to say the same thing, but now I'm saying it externally. So not doing internal language magic. So let's assume that I have a P, which is a strict CWF with pi. So all the equations are definitional. And you can think about this P as presheaves over some category. The notion of a P universe, so now it's not a universe internal to presheave, now we have a P universe, which is closed under pi, starts with these components. So types form a context in P. So if P is the presheaf model, then types form a presheaf, right? Terms are a type in P over red tie. So if P is the presheaf model, then this is a dependent presheaf over the red tie. Then what is the red pi? So it's a morphism in the model P, which goes into the red tie from the red tie extended by this function space. So this is why we assume that the P is closed under pi, because we need a function space here. So this is function space which goes from terms which are which are the red terms, into constant type. So K is just turns a context into a type. Okay, we have to assume that this model is democratic. So this K, I should have said here, democracy as well. And then, for example, Booleans are a tie, so they are a global section of tie in the pre-sheaf model, a global element of tie. Okay, so what we did, I specified all of this now completely externally. And actually, if P is indeed the pre-sheaves over C, then C together with the P universe is almost the same as a model of type theory. What's the difference? Just checking whether the audience is listening. Okay, so it's not about the equalities, it's really just the, okay, so you have to be a bit used to CWFs, I guess, to answer this. So we don't have context extension and empty context here. That's what is missing. But everything else is the same. Yeah. Okay. And then we redo the same model construction that we did on the previous slide now externally. So we call this the P contextualization of a P universe. So in this new model, context will be just context in P. Substitutions will be just substitutions in P. Substitution of types, the action of substitutions on types is now function composition or composition of morphisms in P. Okay. Then now types are like maps from gamma to red tie, and the same for terms. So actually, this is exactly the same as what I had on the previous slide. Exactly the same, but now saying it externally. Okay, and then you can define pi types using this pi universe. Okay, and then finally, you say that what you want is that you want a relationship to the syntax that you start with, which I call I, the initial model, the weak initial model, to the P contextualization. So, and this is just the Yoneda embedding. So Yoneda takes a object in the syntax, and into, if P is the pre-sheaf model, you just get a pre-sheaf from it. So this is the Yoneda embedding. The Yoneda's action on morphisms is just a consequence of the Yoneda lemma, which says that maps from delta to gamma are isomorphic to natural transformations from Yoneda delta to Yoneda gamma. And then you have you want a similar isomorphism for types and a similar isomorphism for terms. And if you have this Yoneda for I and this P contextualization model, then it's almost saying that the syntax is isomorphic to this P contextualization. The only difference is that you don't have that, you don't have an isomorphism for context, but that's easy to fix. You just replace context in the P contextualization by telescopes, and then you even get an isomorphism here. So what we achieved here is that assuming we have this strict, the P strict CWF pi, we constructed, and assuming that there is a P universe and this Yoneda, then we construct a new model, which we call the P contextualization of this P universe, which is isomorphic to the syntax. Okay, it's not merely equivalent, it's really isomorphic to the syntax. And so we are allowed to call it also a syntax. And this is the strictification construction, because this, if this is a strict CWF pi, then the P contextualization model will also be substitution strict. Like, look at how context and substitutions are defined. They are inheriting the strictness from the P. Because substitution is modeled by composition of morphisms, it will be definitionally functorial. because pi types are also modeled by a composition, they will also have definitional substitution rules. So, and the new model that we got, this P, is isomorphic to the original model. And it's very pleasant to work with it in Agda because all these substitution rules hold on the nose. Okay, so what's the issue? The issue is that presheaves over C don't form a strict CWF pi. So actually the CWFs of presheaves is strict. So all the CWF equations in the presheave model are strict. Yeah, I mean, these kind of things are a bit weird because usually people don't think about strictness. We work in extensional type theory when we do meta theory of type theory, and it's you have to like analyze all the previous publications on presheaves models, whether the thing they do is actually strict or not, or you can try to formalize them and see. So, and the fact that presheaves are strict, this relies crucially on strict propositions. So I don't know how to do this without the universe of strict propositions. So strict propositions mean that any two proofs of a strict proposition are definitionally equal. And also you need ingenious trick to define types in this presheave model to make it strict. So actually what you do is what is a dependent presheave? So for any element, any object of the category and evaluation of the base presheave at that object, you get a set. I should have written set here. And then the functorial action, the action on morphisms takes an equality as an input. And this is a trick to make it all strict. Okay, but unfortunately, even if the CWF of presheaves is strict, pi is not strict. So I can show you what the issue is. So this is how pi types are defined in the presheave model. So pi AB at an object I and element of the context gamma I is just terms in the presheave model at Yoneda of I with input A, where YL is the forward action of Yoneda lemma, which takes a gamma I and turns it into a substitution, into a natural transformation, and then the B has to be substituted by this as well. And when you check whether the substitution law holds for pi AB, the issue is that these are definitional equalities, except this one is a propositional equality. You need that Yoneda lemma is, you would need definitional naturality for the Yoneda lemma. So you would need that Yoneda lemma and then post-composed by a gamma is the same as applying the gamma inside. And that only holds propositionally. Or I don't know a way to fix this. And actually, there is another pi type which would be enough for our usage, which is not the general presheave pi type, but pi where the domain is locally representable, but it has a similar problem. So that doesn't solve it. But how we can solve the issue is to use the prefascist sets by Pedro. So they come from a right. The notion of prefascist sets comes from a right conic extension. So there's for any category C, we can take the discretization of that category. We just throw away the morphisms, and then we have a obvious inclusion into C. And we have then the presheaves of C and the presheaves over this discrete category, which is actually the same as just families over C, because the action of morphism is uninteresting. And then there is this right conic extension, F lower star, which takes these families into proper presheaves. And then you can define, prefascist sets are defined by actually some kind of code for a strict presheave. So you say that there is a family here that you start with, that's this gamma. And then you take a sub-presheave of the image of F lower star, and that's what is encoded by this property. So prefascist set is a family together with some proposition over this. Here we also use the universe of strict propositions, and the CWF of prefascist sets is almost strict there's only one equation which doesn't hold by definition, but everything else is strict. So it's very well behaved, and even pi is completely strict. So Yoneda can be defined, and this is what we actually use in this construction. So instead of using ordinary presheaves, we use prefascist sets. And here is our application. So we defined the weak CWF syntax for a small type theory which only has pi and booleans with large elimination. So maybe that's the smallest interesting type theory which has actual dependent types. Here all equations are propositional, so this is a very weak model. We call this model I. Then we formalize the CWF pi of prefascist sets. We defined prefascist sets over I universe, so PFA I universe. A family closed under pi and booleans. We showed that the syntax I is isomorphic to this telescopic version of the contextualization of this universe. This is the Yoneda embedding for prefascist sets, actually. And then, once we know that this is isomorphic to the syntax, it's quite easy to derive the elimination principle, the induction principle for the syntax. And we use this to prove, to formalize for the first time this very beautiful gluing style short version of canonicity. So actually, this canonicity displayed model is also substitution strict. It's a very pleasant Agda code. When we try to compute with it, Agda hangs. So Agda is not yet capable of computing with our beautiful new strict model. And that's it. So I just quickly want to summarize some things which are related to this. So logical frameworks, there the main idea is that you work internally to the presheaf model, and then you figure out how to do proofs about your theory there. This has the same semantics of higher order abstract syntax and as two-level type theory, so these are very related. There's also synthetic taint computability and internal sconing, which are also approaches to work internally to some presheaf language or some glued topos language and to these kind of things. So compared to these, oh yeah, and you should go to the talk by Andras, which is also related. So compared to these, we stay completely external. Our meta theory is ordinary type theory. The only assumption is quotient inductive types, but you cannot avoid quotients if you want to work in a semantic settings. Then there are the generic strictification via conservativity, which could be applied. There's the local universe construction, which strictifies isomorphisms into propositional equalities, but actually it can be also used to get definitional equalities if you start with a rich enough model. And then you have more ad hoc strictification methods, like you could redefine substitution recursively, or you can just use the standard model, which we call shallow embedding, and pretend that it's the syntax, but this doesn't give you an induction principle. So summary, this is my last slide. So we analyze, so you can see what we have done by as an analysis of Hoffman semantics of higher order abstract syntax, but in an intentional setting. And we obtained a method for strictifying substitutions in a model of type theory. And this eliminates the disadvantages of intrinsic syntax or nice abstract syntax compared to extrinsic syntax. It is more abstract. It has more definitional equalities. It still has explicit weakenings, and you work with De Bruijn indices. But that's the same for extrinsic syntax when the typing relation also has explicit weakenings. So that's not really a disadvantage, I think. We conjecture that this rectification method works generically for any second-order generalized algebraic theory. So any type theory or any language with binders, you should be able to do this. There was nothing specific to the theory of just pi and booleans that we used here. I don't know whether we can do this without strict propositions. We want to make it compute and try to formalize it in POC or some other system where maybe it computes better, and to formalize it for larger type theories. Thanks.
Questions for Ambrus? Check the Zoom. Oh, okay, I'll go first then. I wanted to ask you about the last point actually, because as you were talking, I was thinking, okay, how do you extend this to, let's say you have sigma types or whatever? And then at first I thought probably it's straightforward. Then you started to explain how you have a strict CWF, but then as a CWF with pi types, it's not strict. So then I started to get more worried. So like, how do you imagine that this is going to extend to a type theory with more type formers?
Yeah, so it extends very straightforwardly. So here, maybe it's a bit confusing that here I say that we need a strict CWF pi. So that stays strict CWF pi. If you add more type formers to your theory, you don't need anything more of this. So that's our logical framework, basically. That's what is providing the logical framework for me. And then if my model has more type formers, there's no issue. The issue is that here you have very large terms because we have some kind of pre-fascist second order representation of presheaves rather than the original syntactic presheaves, and it seems it's very inefficient if you want to work with this in Agda. Actually, we don't know what the issue is.
Okay, but it's essentially like a bootstrapping thing.
Yeah. Yeah.
Okay. Other questions? Yes, Torsten?
I wonder whether there's a good way to sort of fight this, because in a way, I don't really want to think about strictness. I mean, I want to work in a sort of semantic setting. And then, I mean, what you're saying is that things take place in like a two-level type theory. And the outer level is really part of my implementation. And I work at the lower level, and everything is just semantic, but well behaved syntactically. Does this make sense?
No, I'm not sure I understand the question, but maybe something that comes to my mind. So, you can imagine the strictification, it's an issue with formalization, and there are these generic methods for strictification, like Hoffman's conservativity, which is like a nuclear weapon or something. And compared to this is an ad hoc technique to strictify just this kind of situation. So the kind of situation that this works for is languages with binders and substructural languages. So not substructural, not like linear logic, but like type theory, which is a structural language. And there it works well. And I think that maybe the transport, there is no in my imagination, I think that there is no general solution to transport hell, but there are particular solutions for your application domain. And
I want to problem, I mean, to provide a sort of ready-made solution for the user who works at a lower level, and who doesn't have to think about strictification anymore. I mean, I don't know.
I mean, you could add, so I think that in 10 years, there will be proof assistance with SOGAT support, so second order generalized algebraic theories, which will do all of this strictification for you. And then you just say, here is my language, get a strict first order syntax for me. And then you can work with that directly. And then you can imagine this talk is the semantic justification of such a system.
Okay, and yes, final question then.
Do you have some idea of why computation doesn't work? It's just a problem of rough power, or do you have some insights? Thank you.
No, I don't know.
The expert answer is that
Yeah.
let's end on that, and let's thank Ambrus again.
Thank you.